Hello everyone, welcome back to chemistry. In this lesson, we will learn how to describe the properties of ionic compounds. We'll learn the process of metallic bonding and list and explain some properties of metals. In Schoology, you will find a set of notes where the topic is going to be ionic compound properties, metallic bonding, and metallic properties. Please download that into Notability at this point in time or print it out if you prefer to do it that way. All right, so we're going to be talking quite a bit today and in the next lesson about properties. And we did talk about properties and define them last trimester, but just to bring that back up for us, properties are simply things about an object that you can observe or measure. Okay, so like color or length or width, those are all properties of things. Okay, and in matter, the observable property often depends upon two things: the arrangement of particles that make up the matter and the attraction between the particles that make up the matter. If we apply those two ideas to ionic compounds, here's what we find out. In terms of arrangement, ionic compounds are solids, so the particles are close together, and those particles are in an ordered, repeating pattern. We've called that the crystals. In terms of attractions, in ionic compounds have ionic bonds, right? Those crystals form between because that attraction between the cations and the anions, the ionic bond, is strong. It's a strong attraction and it's far-reaching. It brings all of those ions together even at a distance. So when we think about properties of ionic compounds, these two ideas are going to come back over and over and over again. That ionic crystals have repeating ordered patterns, and that the bonds between them, the ionic bonds, are strong and far-reaching. So the first property of an ionic compound is that ionic compounds tend to be hard, meaning that they resist forces applied to them without changing much. If something is hard, I can push on it, and it doesn't change much. It doesn't squish, it doesn't bend, those kinds of things. Okay, so hard things resist forces applied to them without changing very much. Okay, why would they do that? Well, again, comes back to arrangement and attractions. The ionic bonds between the atoms are very strong, so that means that there's a lot of energy would be needed to move those ions out of position. So they stay in position. So it doesn't squish, it doesn't bend, it doesn't do those things. Those particles just stay where they are. They are hard. The second property of ionic compounds is that they are brittle. Okay? So we just said that they're hard, they resist force a lot. But if you put enough force on them, if you get strong forces on them, what happens is the way that they break is swiftly and cleanly. We sometimes say that it shatters. Okay? This is as opposed to like tearing or ripping. Doesn't do that. It's brittle. It breaks. It shatters. Okay? And the reason for this has to do with the fact that we know that the ions in an ionic compound are ordered. Positive, negative, positive, negative, positive, negative. So if I put a strong enough force on them where I can actually get past those bonds just a little bit, be stronger force than the force holding those ions together, I can actually shift the layers so that instead of having positives next to negatives, I now have a positive next to a positive, a negative next to a negative, a negative next to a positive next to a positive, etc., etc. Well, that means that we have repelling that's going to happen here. And what happens then is the structure repels and breaks apart. That crystal cracks. Okay, so again, strong applied forces shift the layers. We have same charged ions next to each other, net positive next to positive, negative next to negative, causing them to repel. And so the layers spread apart. It splits, it shatters, it's brittle. Third property that's noteworthy for ionic compounds is that they have a high melting point. Okay, so again, what's melting? Well, that's changing from a solid to a liquid. And if it's a high melting point, that means it takes a high temperature to be able to do that. Okay, so again, if we have a high melting point, what does that mean? Well, if I'm going from a solid to liquid, we learned last unit that if we go from a solid to a liquid, we are actually start changing the positions or causing the particles to roll over one another. All right? In an ionic compound, it takes a high temperature, or in other words, a lot of energy to be able to get those particles to roll over one another. Why? Because a strong bond keeps those ions in fixed positions. It likes that strong bond holds them in place. If we get enough heat, you can actually overcome that strong bond and get them to start to roll over one another. But again, it takes a lot of heat energy. And so as a result, a high temperature or a high melting point is needed in order to go from a solid to a liquid. Next property of ionic compounds is that they do not conduct electricity as a solid. So we're going to take a little pause here because we have to understand a little bit about what electricity is. And essentially what electricity is it's electrons moving, okay, through a material. And in order to get something to conduct electricity, in other words, to get electrons to move through a material, two things have to be true. One, there's got to be charged particles, things that can attract or repel the little electrons. So you've got to have other positive or negative charges that can either attract or repel the electrons, thus moving them through. And the second is you've got to have space so that the charges can move through the material. Okay? An ionic compound does not conduct electricity as a solid. Why? Well, does it have charged particles? Absolutely it does. It has positive and negative charges in there, so we should be okay there. But how are those particles arranged? Well, they're very closely packed to one another. There isn't space for electrons to be able to move in between those ions. The ions are very closely packed and stuck into fixed positions, so the electrons can't move. Next property of an ionic compound is that they can conduct electricity if they are dissolved in water. So once again, in order to be able to conduct, we have to be able to have charged particles, and those particles need to be able to move around. Okay, so ionic compounds can't dissolve when they're solids, but they can dissolve can conduct electricity if we put them into a liquid and dissolve them. Okay, because what happens is dissolving separates the ions into the solution. So you end up with the ions floating around in the water looking like this. You'll now notice that there's space between them. Okay, and so as a result of that, the ions can move around and electrons can be moved by the ions moving around and can move through the material. All right, so by creating more space between them and creating the charge, dissolving will separate the ions in solution. The ions can move around. So we have both charged particles and charges that can move around. Okay. This one is kind of interesting. One little piece of this where you see this in real life is if you've ever been in a pool or in a lake in the summertime and there was lightning around, they probably told you to get out. And you probably thought, oh, if that hits the water will conduct electricity. Well, it turns out that water doesn't conduct electricity at all. In fact, if you had a lake or a pool that was filled with absolutely pure water, just straight H2O, lightning or electricity could hit it, and it would not cause a problem with you. Okay? But we know that lakes have lots of minerals and dirt and stuff dissolved in them. Many of those minerals and dirt are ionic compounds. Same thing with pools. We know for certain pools they put chlorine into. Chlorine creates chlorine ions dissolving into our pool. And so then you have an ionic substance in the water and whoop, you can go ahead and conduct electricity. Okay? This is again why they tell you don't be in a bathtub with a hairdryer or with something like that along with you, because again, those things can conduct electricity, especially in our regular tap water that has minerals and things dissolved in it, as well as any of the soaps or salts that are on our body that get in the water as we bathe. Okay. So, properties of ionic compounds again, right? Will not conduct in solid form, but will conduct when dissolved in water. Water itself does not conduct, so it must be the ions that are in there that are allowing electrons to move through and conduct that electricity. All right, those are the main important properties of ionic compounds that we want you to know and know why they happen. And again, all of those properties are a result of both the arrangement of particles in an ionic compound, closely packed together, and the particle or the forces of the attractions between them, the very strong attractions that hold them together. All right, so we've spent better part of about 4 days talking about ionic bonding and ionic bonds. The rest of today, we're going to talk about a second kind of bond, which is a metallic bonding. Okay, so we know that ionic bonds are made when you have a nonmetal and a metal come together. Okay? The metal loses electrons and becomes positive. The nonmetal gains electrons and becomes negative, and you get an ionic bond between them. Okay, so in metallic bonding, we don't have a nonmetal and a metal. We just have metals, which is why we call it metallic bonding. So metal atoms are bonded to other metal atoms by a metallic bond. Okay, so if you think of all kinds of different metals that you may have heard of, steel, silver, platinum, gold, brass, bronze, copper, those are all examples of metals, and the atoms within them are held together by metallic bonding. Let's see how this works. All right. We know from our study of ions that metal atoms will lose electrons to become more stable, to become like their nearest knowable gas. So if I have a collection of metal atoms, like a whole bunch of sodium atoms, they're all going to just start losing electrons, losing a ton of electrons to become positively charged ions. Why? Well, because they don't really want to keep those electrons around. It's more stable if they don't have them. Okay? So all of the atoms in a metal are all metal atoms, and so they're all trying to lose electrons. Nobody's trying to pick up gain an electron. It doesn't help them at all in terms of being stable. So there are no nonmetal electron atoms to pick up those electrons. So you end up with two parts in a metal. You end up with a sea of moving electrons, all of these electrons that have been lost by the metal atoms, and metal cations left over after the business here, after they lose those electrons. So again, we refer to metallic bonding as a sea of electrons model. Positive cations in a sea of moving electrons. Okay. So what holds them together? Well, the metal cations will attract the moving electrons in the sea. So an electron comes between the atoms, the cations, and it gets attracted. This negative electron gets attracted by that cation and by that cation. And since they're both holding on to the electron at the same time, they sort of get connected to one another. Okay? But those electrons are moving around. So that electron will move on, and the next electron will come through. And so these attractions form and then disappear until the next electron comes through, and once again, the attractions form and then disappear as this happens. Okay? So the metal cations mutually attract the moving electrons in the sea. This connects the metal cations through the electron. Those individual little connections, those individual bonds are temporary. They form and they fall apart rapidly as the electrons move around. However, the number of bonds at any one time in the structure holds it together. So you can sort of think of like the pink clouding here as being different attractive forces between the cations and the electrons that are moving in between them. And so you'll notice in some places it's a really strong attraction at a point in time, and other places there's almost no attraction at all. But in general, there's so much attracting going on at any one point in time that it holds the structure together as a whole. All right, so to summarize, in an ionic compound, you have a metal which gives an electron to a nonmetal, giving you a positive metal ion and a negative nonmetal ion. Opposites attract and they come together. In a metal or a metallic bond, you have two metals. They each lose electrons, and then They become positive ions, and those positive ions attract the electrons that are moving around. Okay, so again, positive attracting negative, it just works a little bit differently. One other thing that happens with metals is that you can have metals be pure metals made of just one element, or you can have mixtures of metals that will bond together as well. If you have a mixture of metals held together by metallic bonds, we call it an alloy. So it's actually a homogeneous mixture held together by metallic bonds. Examples of this that you've probably heard of in your life. Brass, like we use to make brass instruments, is actually a mixture of copper and zinc. Bronze, like bronze medals in the Olympics, are made out of copper and tin. Stainless steel, very popular in appliances right now. That's a mix of iron, chromium, and nickel. And 14 karat gold. Pure gold is 24 karat. If you have a number smaller than 24 karat, your gold is actually mixed. Some gold, copper, and silver are what they put into 14 karat gold. And they do that because pure gold is pretty soft. So if you made up jewelry or something else out of that, it would actually like bend and stretch or dent and things like that. So by putting in copper and silver, you can create a stronger metal. And last but not least, titanium alloys. Many of you, if you're an athlete, you might have a piece of equipment that is a titanium alloy. Makes it a very light metal for you to work with, and can oftentimes be flexible as well. And so properties that are desirable in a piece of sporting equipment. All right, so that's metallic bonding. So let's talk about some properties of metals then that happen. Reminder, as we talked about at the beginning of this session, the properties depend upon the arrangement and the attraction of particles. So arrangements in metals, those are the positive cations and the negative C of electrons. The attractions between them, still a fairly strong bond, but not quite as strong as an ionic one because the bonds form and unform. So the very first thing that we need to think about is properties of metal is that they are shiny. Okay, they reflect a lot of light. And this is because the sea of electrons outside of an atom can readily absorb and release energy. So the electrons that are out here, they can take in light and they can release light. And they can do that very, very easily. That light coming in gets absorbed and then it gets put back out as light again. So light coming in, light coming back, that's what makes something a shiny reflective surface. Lots of light gets reflected. Second property of metals, two that are closely related to each other. One is called malleable, another one is called ductile. Malleable simply means that you can flatten it into sheets, like making aluminum foil. Ductile means you can pull it into wire, like making copper wires. Okay? This happens again because of arrangement and attraction. Okay? The sea of electrons allows the metal atoms to roll over each other when enough force is applied. So if I apply enough force to this, I can actually just pop these cations into new positions in the sea of electrons. And as a result of that, you can end up with a situation where you change the shape of the metal and by changing those positions. When you change the shape, you can do things like flatten it out or pull it into a new shape of a wire shape. Okay, so again, the fact that there's some mobility of these cations, these metal cations in the sea of electrons that allows them to move over or bump each other out of the way makes metals malleable, flattened into sheets, and ductile, able to be pulled into wires. Next property of metals we want to be aware of are high melting and boiling points. Okay, not as high as ionic compounds, but still high. Okay, why? Well, remember when we talked about melting and boiling for ionic compounds, we said it was the strong bond, and it took a lot of energy to break that strong bond and get the atoms rolling over each other or separating from each other to become a gas. All right, so same thing is true in a metallic bond. We still have a strong bond. Metallic bonds are strong, not quite as strong as ionic bonds, so it's still going to take a lot of heat energy to disrupt the bond and make them shift positions or break apart. In general, the melting point of a metal is a little bit less than than a generic ionic compound, although that's not always true. Last but not least, characteristic property of metals is metals will conduct electricity. Again, remembering when we were talking about particles at the beginning of this lesson, in order to have something conduct electricity, you've got to have charged particles. And number two, they've got to be able to move through the substance. Do we have charged particles in a metal? Yep, we have the metal cations and we have the sea of negative electrons. So that one's taken care of. Can electrons move through the substance? Well, yeah, we said the sea of electrons was already a moving set of electrons that are moving through the substance. And so we do know that we can move electrons through. We are able to do that. So electrons in the sea are able to move freely, so electrons can move right on through the metal. All right, so that's it for this lesson. Please go ahead and make sure you complete these notes and submit them to Schoology. And then when you are done with that, in Schoology, there is a short ionic and metallic quiz that you should use these notes to try to answer, just to check your understanding. Have a great day.